Hello, welcome to Computer Graphics Rendering. In this video, we're going to talk about ray tracing. Let's look at an overview. We want to talk about what is a ray? Ray-sphere intersection. Camera rays. Weighted ray tracing. And finally, programmable ray tracing. So, what is a ray? Well, we know that a vector represents three numbers, x, y, and z. A ray, essentially, we are interested in a starting point, and it has a direction associated with it. So sometimes we'll call this the origin of the ray, and we'll call this second part the direction of the ray. So essentially a ray can be thought of as a pair of numbers. We'll just call it O and D, which are two vectors, or 3D position, if you include the origin. Another way to think about a ray is as an equation. For example, we are interested in representing points along a ray. So we might use a variable called t, and we will say that a position, or p, equals the origin plus rt times the direction of the ray. And this allows us to set different points along the ray, although theoretically you could have points behind the ray if you have negative t values, or these are positive t values if we're talking about the positive side of the ray. Now, let's talk about ray-sphere intersection. And we could actually be talking about the intersection of a ray and any kind of an object. But in this particular example, we are interested in what happens if a ray has one of three cases. Those three cases being, you have intersection on the edge, a miss, and where you could have multiple hits. And theoretically, you could also have the case where you have a ray, but your object is behind. And we're going to see this case in just a second. Okay, so the idea here is that we can use the equation for a ray, which we call P equals O plus T times D, and we can use the equation of a sphere, which if we have a radius, it's radius squared plus or equals the XYZ components of the center of the sphere, and or not the center of the sphere, but this equation is satisfied. In other words, if x squared plus y squared plus z squared equals r squared, then that represents the surface of the sphere. So if we want to incorporate a location for the sphere, if we're going to use a vector format, we might actually say that r squared equals the dot product of any point on the sphere minus its center with itself. And it shouldn't take too much convincing to show that that's essentially the same idea as the previous example. However, if we make a slight modification here, we're going to just change this so it's a little bit more correct. And we're going to say that this is a function of t. So the origin plus t times the direction. We can take our equation here, r squared equals some function of p of t minus the center of the sphere, dot product with p of t minus the center of the sphere. And expanding this out even further, we are basically trying to set this up so it looks like a quadratic equation. And so if we do some math on this, we will find that we can get t squared times the direction dot the direction plus 2t times the origin minus the center, dot product with O minus the center, plus the center, dot the center, minus r squared. And so if we put this in a quadratic form, we will see essentially that since we know d dot d and o minus c dot o minus c and c dot c minus r squared, then we will have our a will equal d dot d, our b will equal o minus c dot o minus c, and our c will equal c dot c minus r squared. And we know that the quadratic equation says that x will equal minus b plus or minus the square root of 4ac over 2a. I'm sorry, this value here is the square root of b squared minus 4ac, which is called the discriminant. And so if we solve this equation, I guess not for x but for t, then we will get one of these three situations. Either the discriminant will be less than 0, and you will get this case where you have a complete miss. You will get the same value for t, in which case you have only one intersection, and you will get two different values for t. In other words, you have two intersections. Now, if your t value is positive, then you know that it lies in front of the ray, and if t value is negative, it will be behind the ray, in like this case. And I just noticed this should actually be 2 times o minus c dot o minus c, because we have 2t times o minus c, o minus c. So now that we know how to do some basic ray sphere intersection, we need to know how to generate camera rays. And the way that camera rays work is, given a camera, we essentially would like to send pixels or find out what the color of pixels are. So if we had a very simple 2x2 grid, we would send a camera ray out to this pixel, to this pixel, and this pixel. And then what we're going to do is check for intersections. So first we generate a ray for every pixel. And then we will check for intersections. And essentially what we can do is maintain a list of objects and just go through them one by one and see if we had an intersection. And so if there's an intersection, then we'll shade the object. And if no intersection, then we can calculate a different color, such as the sky. So this is what I just described. Essentially is called ray casting, and ray tracing is a little bit different. Ray tracing can be thought of two ways. First, we're going to think of as weighted ray tracing. And weighted ray tracing, so we have this classic image that was rendered by Weighted, and essentially solved three main problems. The first problem was reflection, refraction, and shadows. And in fact, all three of these things are big problems with real-time rendering because there's no straightforward solution. And what weighted ray tracing does, though, is make each one of these types of effects easy to achieve. So the idea is that if you have a camera and you send out a ray into the scene, and let's just say that you hit a sphere, essentially you can calculate three rays. So you could have refraction, you could have reflection, and if you had a light source, you could also check for shadows, right? So because we have an intersection here on the way to the light, that technically would be in shadow. However, if you had another light over here, then of course you would be lit. And this is how weighted ray tracing essentially works. So we basically branch off three different kinds of rays. So shadow rays, refraction rays, and reflection rays. Now there are some variations. So for example, we don't have to shoot the rays from the camera first, which is technically called backward ray tracing. And backward ray tracing is where you start from the camera and get your way to the light. And forward ray tracing is where you start from the light and you work your way to the camera. And another approach is bidirectional. In other words, what we want to do is start from the camera and the light and try and find connections in between somewhere. Now, weighted ray tracing is pretty interesting, but it's also pretty well understood. And but it doesn't necessarily play well necessarily with programmable shaders. So we're going to take a look at a new concept, which is programmable ray tracing. So let's talk about programmable ray tracing. And this is essentially the architecture for the new DirectX 12 ray tracing. And the way that this works is we have a step called ray generation. And this will basically create rays. And this goes into some sort of acceleration structure. This could be like a bounding volume hierarchy or something like that. But if you have lots of objects, you want to efficiently go through them. Maybe it's a voxel type grid. It could be any number of things. We're just going to leave that abstract for now. And the idea here is that we have a few use cases. So case number 1, we want to check for intersection. And then we might want to just do something. If we find any intersection, we'll call this an any hit shader. And any hit shaders are kind of good for like shadow rays, for example. If we shoot a ray and anything hits between the object and the light, then we know that there's a shadow. The next thing is, as we're checking for intersections, we're asking the question, well, did we get a hit? If we did not get a hit, then we will want to call a miss shader. In other words, maybe this could be our sky model or something. And then, but if we did get a hit, then perhaps what we want to do is call a closest hit shader. And these shaders are probably going to be the most expensive because we're calculating BRDFs, so complex lighting calculations. And essentially, a lot of these shaders, like the closest hit shader, can actually spawn new shaders. Or actually new rays. Which makes sense because if you're doing a reflection ray, then we would want to go ahead and, for a BRDF, like a shiny BRDF, we would want to spawn a new ray for that. So this is an example of programmable ray tracing where we try to abstract that previous slide with its style ray tracing, but make it applicable. So this can be extended to do path tracing, simple ray tracing. This could be this could be used for extending maybe a real-time renderer if we want to just kind of only shoot shadow rays out or only shoot reflection rays or refraction rays. So in this sense, this generic programmable ray tracing could be used to augment an existing real-time renderer, or it could be the basis for a pure ray tracing solution. So that's about it for this particular video. So just to recap, we talked about what are rays. We talked about ray-sphere intersection. We also talked about how camera rays work and how you might want to have a list of objects to check intersections against, and how we want to essentially create a ray for every pixel, which is called backward ray tracing when we start from the camera. It's called forward ray tracing when we start from the lights, and it's called bidirectional if we're working both ways, cameras and lights together, and finding connections in between. Then we talked about weighted style ray tracing, and then talked about how the emerging programmable ray tracing kind of works and the basic pipeline for that. So, as always, thank you for watching this video, and adios.